Следующий у нас Aditya Narendra, using multitask reinforcement learning algorithms for multifunctional robots.
So, hello, I'm Aditya. I'm third year student at Moscow Institute of Physics and Technology. And today I'll be presenting my research on using multitask reinforcement learning algorithms for multifunctional robots. So, first of all, let me introduce the multifunctional robot of our choice, which is Mobile Aloha. It is one of the new groundbreaking multi-control robot developed by the researchers of Stanford and Google. Basically, its application, given its design and capabilities, it is suitable for a variety of research and even household works. So, first of all, it is it has the manipulation capabilities. So it basically has two different manipulators and as well as navigation capabilities. So it is basically a bimanual mobile manipulator. So first of all, it has two cameras which are mounted on the wrist, like on the manipulator, and it depending on the setup, it can have a third camera or a LiDAR sensor. Now, this robot is so groundbreaking because it can perform a combination of tasks, for example, both navigation, manipulation, such as picking and placing, as well as maneuvering through complex environments and performing tasks that require a very high level of coordination between like seeing and manipulation. So this is particularly used in research purposes, for example, and also it can be used for household work. As you can see from the video, it can perform different type of tasks like manipulation tasks. It can cook, clean, all that. This is basically right now this robot is first of all, it has 2 degrees of freedom for the base. So it has 2 wheels, and it has 14 degrees of freedom for the manipulators, so like 7 each. And these manipulators are Viper X 360 manipulators developed by AgileX Robotics. And currently the researchers are using ACT for making it autonomous, which is action chunking with transformers. And although it's a really good approach for these kind of robots, especially if you have some high precision tasks, it can perform it really well. But if you have some other tasks which are long horizon and maybe they're a combination of different subtasks, ACT can be a bit ineffective in that case. So the idea of our research is to use reinforcement learning instead of ACT to see how well these algorithms perform when used with Mobile Aloha. And in particular, we are using multitask reinforcement learning algorithms and also comparing them with the single task alternatives. So next, let me define the problem formulation for our research. So for the environment, as a basic environment, we are using MDP, which is Markov Decision Process Framework, and it's a very common approach in reinforcement learning. And MDP basically contains state space, and it represents all the possible configurations and statuses, for example. So in our case, it can be the robot's spatial coordinates and maybe the orientation, the velocity, and the state of the manipulators. So for example, if the gripper is open or closed, and what is the position of each joint of the manipulator, and maybe if it's a manipulation task, we might also have some object position that we want to manipulate and all that. Next, it consists of all the action space the robot can perform, including navigation. So in our case, we are using angular velocity and linear velocity for robots base, and for the manipulator control, we are using basically the torque applied on each joint. And also for the gripper, we have a single state which tells us if the gripper is open or closed. Next, we have the reward, and the reward function is defined for each experiment separately, and we will discuss more about it in the later slides. So basically, we also have terminal conditions usually in MDP, which tells us if the task is complete, or maybe if we have some maximum episodic time step. Then if the time step is reached, then the terminal condition is reached, basically. Next, we have a goal for each task. The goal is to find a policy. Policy basically maps a state to an action, and the idea is to find the policy which gives us the maximum cumulative reward over some certain horizon. Next, we will define some baseline RL algorithms. So here we are using PPO, which is developed by OpenAI. It is a single task on policy algorithm. SAC, which is also a state-of-the-art single task off policy algorithm. And we have Dreamer v3, which was pretty groundbreaking a few years ago when it was the first reinforcement learning algorithm to mine diamonds in Minecraft without any external human help. So it has been the go-to choice for multitask algorithms. And the third is TDMPC2, which is temporal difference model predictive control. It is actually a new algorithm developed by the researchers of UC San Diego, and we will discuss more about it later, but let me tell you that it is also a multitask algorithm, and it is off policy, similar to SAC. So the idea behind using these algorithms is that first we want to compare how effective single task and multitask learning is in terms of multi-control robots, because usually if we have a multi-control robot, we separate the controls in form of base and manipulator. And of course, it can be useful and efficient in some cases, but I think there should be an approach of using multitask algorithms here, so that we can make the training process more streamlined. So basically, we want to compare single task and multitask learning, and a single task approach basically involves training an algorithm for a particular task, so maybe picking up or navigation, something like that. And however, its ability to generalize to other tasks may be limited, as I said already. So this is not good it's not that useful when a robot like Mobile Aloha is using these algorithms, because it needs to perform highly specialized tasks where precision and optimization is a key, and usually the tasks performed by Aloha can be very complicated, and it could be divided into some subtasks, and in this case, single task algorithms might not be as good. So in contrast, we can use multitask learning, which involves training a model in multiple tasks simultaneously. And this method develops a more general skill and broader understanding of which can be more efficient in terms of learning time and resources, since the model can share the knowledge across different tasks. We can even train the model on some particular tasks, for example, picking and placing separately, and then the model might be able to perform a pick and place task without actually learning it. Similarly, we can train the model to perform manipulation and navigation separately, and then the model might be able to perform mobile manipulation. So in this sense, multitask algorithms are very useful for robots like Mobile Aloha or any other multi-control robots. Next, we have off-policy and on-policy algorithms. And policies such as PPO learns a policy based directly on the actions taken by the policy itself. This basically means that they consistently evaluate and improve the policy, whereas the on-policy algorithm has advantage in the sense that it reliably improves upon policy it uses. So other than that, we have off-policy algorithms like SSC, Dreamer v3, and TDMPC2. And these policies can basically learn from different data and not directly from a single policy like on-policy algorithms. This means they can learn a more broader range of experiences, including some older policies or even some hypothetical scenarios not taken by the current policy. So this can help in faster learning since the algorithm isn't generalized. Although if we talk about vectorization of training, this can lead to some performance fluctuations because there would be different spaces and each spaces would have its own formulation of the policy. So it can cause slight problems, but it's still very effective for single non-vectorized environments. So next we will talk about the hyperparameter tuning for our experiments. So for TDMPC2, the main idea behind it is that we can use the same set of default hyperparameters for all the tasks and without any tuning, without any task-specific tuning. Whereas for Dreamer v3, we chose the S model size configuration, which is basically the equivalent of 1 million parameters as recommended by the TDMPC2 authors. And Dreamer v3 has I think 4 configurations: XS, S, large, and extra large. And we chose small model size because it's the most balanced one. For SSE, we use the parameters used from the Article 3, which is the original TDMPC paper. So basically TDMPC2 is based on TDMPC1. And in both the papers, the authors have compared SSC and TDMPC for different types of tasks on using DM control, Maniscale, and MetaWorld. And these also include some manipulation and navigation tasks. So we directly took the hyperparameters of SSC from that paper. And for PPO, we used Raytune from the RLib library. And it is a very standard library for hyperparameter tuning, and it provides a really good task-specific configurations for hyperparameters of PPO and even other algorithms like Dreamer v3. But in our case, we are using the actual implementation of Dreamer v3, so we didn't use RLib. Since TDMPC is a very new algorithm and people are not as familiar with it as compared to Dreamer v3, SSE, and PPO, which are state-of-the-art baselines. So let's discuss a bit more about TDMPC2. So basically, all components of TDMPC2 are implemented as MLPs with intermediate linear layers followed by layer norms. And it also has mesh activation, and to mitigate the exploding gradients, they basically normalize the latent representation by projecting some Z into the fixed dimensional simplices using some softmax operations. So in simple words, each component of TDMPC2 is implemented as a MLP, and we have encoder, latent dynamics, reward, and terminal value. So let's start with the encoder. It basically maps the observation to their latent representation. And let me also tell you one thing: the main difference between Dreamer v3 and TDMPC2 is that in Dreamer v3, we get the latent dynamics from the observation, whereas in TDMPC2, once we get the latent dynamics, we have an implicit world model. So for each observation, we don't have to reconstruct it, but Dreamer v3 has to reconstruct the explicit model, which makes it much more slower than TDMPC2. And this is why we will see later why TDMPC2 outperforms Dreamer v3. So basically, we have the encoder, which encodes the observation into latent representation. We have latent dynamics, which basically gives us the forward dynamics of the model. Then we have reward prediction MLP, which predicts the reward of a transition. And then we have terminal value, which predicts the discounted sum of the rewards. And finally, we have the policy prior, which predicts the action that normalizes the maximum discounted return. So from the figure, we can see how it works, how the architecture of TDMPC2 works. We get the observation in form of S1, which is encoded, and then from that we use the latent dynamics to predict the action, reward, and the possible cumulative discounted reward over some certain horizon. Next, I want to discuss about the policy prior of TDMPC2. It basically tries to map the policy to a Gaussian distribution, and here the mean is basically the best possible action that the agent thinks it should take, and the standard deviation is basically how confident it is with the action. And we basically try to maximize the mean, and we try to find a balance with the standard deviation, because we don't want the standard deviation to be too big, then the agent wouldn't be confident in its action at all, and we don't want it to be too small, because in that case the agent wouldn't try to explore different type of possibilities. So this is it about TDMPC2, and next we will discuss some of the experiments that we did to compare the different models. So first we tried navigation with obstacle awareness, and for the experiments we used Mujoko, and it is the go-to library to use when we are trying to compare different type of RL algorithms or different type of environments, different type of experiments, all that. And for the navigation task, we basically have the robot and its initial position is randomized at the start of each episode, and it needs to reach a target position which is static across all the episodes, and here the target position is the table, and the robot needs to maneuver around the obstacles, so it shouldn't collide with the obstacles, obviously. And we describe the reward function as the distance between the difference of distance between the initial position of the robot from the target and the next position of the robot from the target. And then we add some reward for the goal. So if it reaches the target, we give it a big reward, and if it doesn't reach, and if it collides with the obstacles, we basically subtract some reward. We give it a negative reward, basically. And here we are using indicator function for checking if the robot is colliding or not. I mean, just for mathematical representation. Next, we have manipulation task. So the task is basically to pick up the cube to a certain height, and it's more or less, the reward function is similar to the original to the navigation task. So here we have the distance of the cube from the initial position of the cube to the final required position, and we give it a positive reward if it picks up the cube, and then we give it some more reward if it picks it up to some certain height. And that's basically it for the manipulation task. And basically to randomize it, we just randomize the position of the cube, of the target cube, and also the height that we need to lift the cube up to. So we discussed two tasks, two main tasks that mobile Aloha can perform. One is navigation and one is manipulation. But mobile Aloha is mobile manipulator. So we want a combination of these two tasks, so which is basically mobile manipulation. So here the robot performs mobile manipulation, which is it picks up the target cube from a certain position, and then it has to place it at another position, which is much further from the initial position. So basically the robot is forced to do some navigation in this case. And here the reward function is basically the combination of the manipulation and the navigation tasks. So next we will discuss some results. So as you can see, we have we evaluated the trained models of the four algorithms, and basically we can see that TDMPC showed promising performance across multiple tasks. And as I already mentioned, we didn't do any task-specific hyperparameter tuning for it. And one more thing I wanted to add, that for navigation, we have only 2 action dimension and 16 observation dimension. So 2 action dimension basically is the action for the wheel, so the angular and the linear velocity. For manipulation, we were using only a single manipulator and not by manipulation. So we had action dimension of 7, 6 was for the joints, and 2 and 1 for the gripper. And for pick and place, we have the combination. So in total, we have 9 action dimension. And as we can see, as the action dimension increases, which means the environment gets more and more complex, TDMPC2 has more or less the same performance, as you can see from the red line. And for the navigation task, SAC, which is SSC, it had almost comparable performance to TDMPC2, but PPO, which is it is mainly used for navigation, it has really good performance as compared to TDMPC2, whereas Dreamer V3, it performed the worst, but at least it was converging more or less. And as we move on to the manipulation task, we can see that PPO starts performing worse, and TDMPC2 has consistent performance, and SAC has more or less consistent performance, but of course its performance is also decreasing. And for the third and final task, which is the most complex one, we can see that Dreamer V3 doesn't converge at all. And it could be contributed to the fact that maybe it has some bad sampling, or it performs better in some benchmarking environment and not in the custom environments like this. And overall, we can conclude that TDMPC has more or less very consistent performance over all 3 experiments, even when the experiments are getting more and more complex. Lastly, we compared the single task TDMPC2 agent with the multitask TDMPC2 agent. We used the data from the replay buffer of the single task training, and we trained the agent for 3 million interaction steps, and it is basically 1 million interaction steps for each task. And more or less, the performance of multitask TDMPC2 is similar to the performance of the single task one, which is really impressive, because usually it is a trend to see that multitask agents don't perform as well as single task agent for some tasks, for some specific tasks. So from this, we can conclude that although although reinforcement learning has a lot of potential in being used for robots like mobile Aloha, we still have a long way to go. We still need some work. For example, using algorithms like TDMPC2, we can make everything much more streamlined, and we can get very precise and efficient performance, even using the multitask models, and the performance would be comparable to the single task models. And I think this is really impressive, and I guess that's here we have some references for the original TDMPC2 paper. I would recommend checking it out because it's a really interesting paper, and I also added some references for mobile Aloha robot. So that's it for my presentation. Basically, if you have any questions, feel free to ask.
Thank you for your presentation. It's really interesting, especially that we now have such a mobile manipulator. I mean, this mobile Aloha robot that is really low cost, and yes. Actually it can perform similar like human. Yes. I mean, it can navigate in some environment. I mean, move from point A to point B and manipulate some objects on table. Maybe reach is not excellent like in human. It can't pick something from the floor, but still it's really promising. And my question is about this TD-MPC approach. What does it have some drawbacks and hidden problems that you saw from your experiments, or is it like really promising and flawless?
I mean, of course, every approach has some kind of drawbacks. With TDMPC2, first of all, since it's very new, it's a very novel idea. So there hasn't been as many experiments with real robots. And secondly, it is, as I mentioned, off-policy algorithms. So it can be a bit, it wouldn't perform as well in the vectorized environments as compared to on-policy algorithm like PPO. Since off-policy algorithms by nature have vectorization order of very less, and on-policy algorithms can have order of like 1 million, so they can vectorize really well. So any other questions?
And would you like to deploy this model on real mobile Aloha? Or do you have one in your university, for instance?
I mean, in my university, we don't have a mobile Aloha robot yet, maybe in future, but of course, if possible, I would like to test different kind of algorithms. For example, I would like to compare ACT with reinforcement learning, see which one performs well and how well they compare to each other. So if possible, then why not?
I see. And regarding the computation resources, can you share what GPU did you use, how long did you train this model, and so on?
So basically, for our experiments, we ran the experiments like 3 times. We ran the evaluation 3 times. The GPU I was using is 2060 RTX, and Dreamer v3 is implemented on JAX, which is much more faster than PyTorch. And so Dreamer v3 had it was basically training in a much more faster time. And TDMPC2 was second in this case. It took me like 3.5 hours to train it in over 1 million interactions for both navigation and manipulation tasks, which is really good because manipulation tasks are much more complex and you would expect it to take much more time for it. But no, it had similar performance, consistency, and it was also training in much more like almost similar time. For SAC and PPO, they were much less efficient in this case. It took me like 5 hours to train them, and evaluation also took me like much more time compared to TDMPC and Dreamer v3.
Okay, I see. Thank you. We got a question from Dmitry Yudin. What limitations on dataset or environment to train TDMPC2?
So one of the limitations might be that right now we were using Mujoko, for example, and it's a natively non-vectorized environment. But for vectorized environment like Isaac Simulator, TDMPC2 might not perform as well. And that is, like, as I already mentioned, one of the drawbacks of this. And also the original implementation of TDMPC2, it has 2 different branches, basically. One is where it supports episodes, like finite episodes, and one where it supports vectorized environment. So if we want to use TDMPC2 with some realistic simulations like Isaac Simulator, we have to adapt it using we have to adapt it customly, and we can't just use the original algorithm for it.
Okay, I see. Thank you. We actually are running out of time. Really thank you for your presentation, and hope to see you next year. Thank you.
Thank you for having me.